Hi everyone and welcome to my YouTube channel. We're continuing with the Cauchy's inequality. In the last video we discussed the statement for Cauchy's inequality. We also discussed the Tito's lemma and we solved some beginning examples. We saw how to apply Cauchy in reverse and we saw a nice trick for Tito. In this video we'll be just discussing 3 other examples and we're going to illustrate very important concepts. So I hope you guys are excited. What are we waiting for? Let's get started. So our first example is an IMO question. It's IMO 1995, question 2. This question, we're given 3 positive real numbers and they're giving us this condition ABC equals 1 and we need to prove sigma 1 over a cubed times b plus c is greater than or equal to 3 over 2. Okay, how can we handle this question? So right now you can see that we have a condition ABC is 1 and we have like fractions here and this thing is greater than or equal to 3 over 2. So how exactly are we going to handle this one? You can see that the denominator is mouthful. We have tons of stuff, a cube and b plus c here. So how are we going to handle the denominator? And of course we need to keep in mind that ABC is 1. So usually one very nice idea is to homogenize to get rid of the condition ABC equals 1. There is actually a trick to homogenize this condition always, ABC equals 1. But we're going to discuss that later in another lesson. Right now, this question actually, we can do it without homogenizing. And basically, you should keep in mind that it's not always a must that you should always, any condition, you should homogenize it and then solve the question. Sometimes it's actually an ugly thing. Sometimes you can just solve the question without homogenizing by simply using, some properties here. So let's think about this question here. Right now we have here a cube and b plus c. As we said, the denominator is full of stuff. We have this complete a cube and of course we have this b plus c as well. So what can we do here? Here actually we're going to discuss a very nice idea. It's common, this idea. The idea is simple. You have ABC equals 1. Since we have stuff in the denominators, our goal is to make them above in the numerator. How do we do that? Very simple. Instead of playing with ABC, we're going to play with 1 over a, 1 over b and 1 over c. So if you just set x to be 1 over a, y to be 1 over b, and z to be 1 over c, then guess what? We still have xyz is 1. So the condition is still preserved. But now you will see that everything is nice because now the a cube is going to become here in the numerator, which is super nice. And you see that it did not cost us anything. So now let's rewrite our inequality in terms of xyz. Now this thing is above, so now we have an x cube there. And now of course we have 1 over y plus 1 over z. This thing of course is y plus z, and we have yz above. So we can just do this. And this thing is y plus z. This thing is greater than or equal to 3 over 2. But remember, we have xyz is 1. So instead of having this, let's erase this, and now we just have this thing. Now this thing is really, really nice, and in fact, you should immediately see that this thing is the literal application of Tito. So now you should immediately go for Tito because you have here x squared, right? And you have a fraction. So immediately we should think about that. So let's just do that. So the LHS is greater than or equal to sigma x all squared divided by 2 sigma x. Of course they cancel, very nice. So we have sigma x over 2. Of course our goal is to show this thing is greater than 3 over 2, which is a piece of cake by AMGM. So this is true by AMGM because you know that xyz is 1. That means sigma x is automatically greater than 3. Beginner stuff. And this thing, of course, we apply T2 here. So that's it. This IMO question is really not difficult at all. The whole idea was this trick. You have ABC equals 1. Then if you just, deal with their reciprocals, then you can simply manage to make stuff more beautiful. And of course, then you should apply T2 at once. Okay, so now we're done with our first example. Let's move on to our next example. So our next example, we have 3 positive numbers, and we need to prove the following: sigma a over 2a plus b is less than or equal to 1. That's it. Okay, what can we do here? Looking at this, we can see it's a fraction. One idea is to apply T2 because we have fraction here, and of course we don't have a square here, so what we can do is multiply by a above and below, so something like this. However, if we look here, then this will disappoint us because of course T2 you need to have it's greater than or equal to something, not less than, so we should delete this idea from our mind. So it was really close to T2, but we cannot do it. And here comes a very, very important idea you should always keep in your mind, which is, look at this fraction. As you can see, you have an a here, you have an a here. So there is a very important idea, which is to do a partitioning of the fraction. You can always partition fractions, especially when you have like the numerator and denominator kind of something is common between them. So how can we do that simply? We can just do this. We can multiply this by 2. So we just need to now show this thing is less than 2. So now we have 2a and 2a. So now we're just going to add a b and subtract a b. So basically this thing is just 1 minus b over 2a plus b. Of course, now you can move this to the right hand side, and this becomes 3. So minus 2 is going to become 1. So now we just need to do this. And now the previous idea we discussed, T2, is now like available, because now you can do this. B squared and b squared plus 2ab. Of course, I just multiplied by b both numerators and denominators, the standard trick of Nisbet, if you remember in the previous video. And now we can say that the RHS is greater than or equal to by T2. You can apply it, get sigma a squared divided by sigma a squared plus 2 sigma ab, which is just equal to 1, because this thing is of course the sigma a squared. And we're done. That's it. So this thing is just by T2. So what did we learn in this question? This idea is very important. You're going to face it a lot in your inequalities journey and math Olympiad journey in general, algebra especially. The idea of partitioning fractions. It's very important to always, when you see something like this, you should know that you can always partition fractions. So here we wanted this to be on this side, so we couldn't. So the best idea, if we partition the fraction, then now we can move it here, and now we're good. Okay, so far we've discussed 2 ideas. The first idea, the IMO question, it was how to manipulate a variable which is a, we made it 1 over a, and here we learned to partition fractions. Okay, our last example for today. is the following. Given 3 positive real numbers, we need to prove the following inequality. Sigma root x over x plus y is less than or equal to 3 over root 2. How can we handle this one? Let's see. Okay, as you can see here, of course it's homogeneous, we don't have any condition. We have a sum of roots of fractions. This thing is just less than 3 over root 2. So how can we handle this? How can we maximize the LHS? Of course, you should think about Cauchy in reverse here, because we have something like this, and we want to maximize it. So how exactly can we do that? Well, you can think of different ideas here, because this thing is already something like root x times 1 over root x plus y. So you can simply try to use Cauchy here and make this less than big root and sigma x times sigma 1 over x plus y. But now actually you will see that this thing, it will not work, because like you cannot really bound this from above, like sigma x times sigma 1 over x x plus y. Basically this thing, I guess it's going to be sigma x plus y x plus z divided by pi x plus y, and of course this thing here is just going to become sigma x squared plus sigma xy, 3 of it, divided by pi x plus y times sigma x. And here automatically you will see that if you expand these guys, you're going to get an x cube, sigma x cube. However, here you're going to just get sigma x squared y, and we all know that sigma x cube is always much larger than that. So this thing is really, you cannot make it less than something, because as we said, the x cube here are going to be big trouble for us, since nothing will cancel them from here. So this idea unfortunately is a bad idea. So we were not lucky in our application for Cauchy here. So what can we do? Okay, one actually common idea to do here, of course before expanding, because we also can expand here, since we have x plus y and y plus z and z plus x, we can just multiply by that and clear the denominators. But before that, there is one important idea you should keep in mind, which is simply T2. Remember, we can do this. So that means we can do this and this. And this is actually a nice tool to get rid of roots. So for example, that means that sigma, if you have roots, let's say first of all roots, if you have any roots, then you can simply do this, which is actually a nice thing, like a nice way to maximize sum of roots. If you have sum of roots, then you can just make it a single root, a root of 3 times the sum. This is actually a nice idea. If you try to do it here, we're going just to get that the LHS is less than root 3 sigma x over x plus y. Now if you think about this, this will cancel, going to have root 3 here and 3 over 2. Basically, if we just square both sides, we're going just to get 3 over 2, like that. Unfortunately, this thing also does not work. You can check it. For example, here you can try partitioning the fraction, like adding y and subtracting a y, and if you do it like this, now actually if you try to apply T2 here, this thing, I'm just doing the standard trick of multiplying by x and x here, so you'll see that the RHS is greater than this plus sigma x1. So now if we can do this, then we will be done. However, the problem is when you multiply 2 by this, you're going to get 2 sigma x square. When you multiply this, you're going to get 3 sigma x square. So that means you're going to have sigma x square on the lower hand side, which is very bad. So again, this thing unfortunately it did not work, although we really have very nice stuff. But this is actually a common case for you in inequalities, that you everything like is nice until the last inequality is exactly the opposite. So this is a bad idea, unfortunately here. However, this idea you should keep it in mind. It's a great tool to maximize sum of roots. Keep it in your mind. By simply T2, applying T2 in reverse, you can always do that. Okay, so we tried many ideas, they all failed us. So now the only idea we're going to do is just the simple expanding idea. So our inequality is the same as sigma root x times x plus z times y plus z is less than 3 over root 2, and we have pi root x plus y. That's it. Okay, so how can we handle this one? Well, again, as we said, we have sigma AB. We can maximize it using Cauchy. But how exactly are we going to choose our AB? Like here you have 3 variables. So should you pick, these two together or these together? Well, here an intuitive way is actually to pick x with y plus z and this one alone, because here you're going to get sigma xy, right? Which is something that seems less like small. If you do this, you're going to get sigma x square, which is something a little big, so you don't really want it to be on the smaller hand side. So that means what we're going to do is we're going to catch the LHS and apply Cauchy. And as we said, we're going to consider this thing as one number. So the LHS by Cauchy is less than sigma x y plus z times sigma x plus z. Of course, all under the root. Don't forget that. Of course, we can, write this as 2 sigma xy here and 2 sigma x here. So basically, it's just 4 times that. Okay, now our goal is to show it's less than this. So now we just need to show you can just delete the roots, square both sides, and you're just going to get, we can just bring the 2 there, 8 sigma x1 times sigma x is less than 9 pi x plus y. Okay, let's see how we can do this one. Well, simple expanding. If you remember, in the very first lessons in this playlist, we discussed that these are really nice because they're both like some identities you should keep in mind. So for example, the expanding of this, we said that it's okay, let's put the 8 here. This is just sigma x square y symmetric plus 3xyz, and we said that this one is very similar. It's in fact the exact same thing, but instead of the 3 we have the 2. Okay, so now it's very easy to, you know, expand this thing, and you'll see 8 here. Here we have 9, so this is the same as the right hand side having a single symmetric x squared y. And now we have, you know, 8 times 3 is just 24. Here we have 18, so now we have 6 xyz, and of course this is correct by AMGM on all of them. And of course we applied here Cauchy. Alright, that's it. So this is the correct application of Cauchy that cracked this problem. Again, what was the idea? The idea was we tried many ideas here. We tried Tito to maximize the sum of roots. We tried Cauchy on this and this, but both of them failed us. So the idea was simple. We just expand everything, clear denominators, and then we choose wisely that these guys as one number and this is one number. We applied Cauchy. Remember, Cauchy is always a great tool to get rid of the roots, and whenever you want to maximize something like sigma AB, it's a great tool. So we just did that, and we just need to show this, and this is really a piece of cake. Alright, my dear friends, so that's it for today. Alright, so as a summary, today we learned some new techniques. The first technique was how to manipulate variables. Like sometimes you shouldn't just go and brute force, you know, homogenization. Sometimes you can just do it by manipulating your variable. So here we had everything below, so we can simply put them above in the numerator by simply doing this manipulation, and everything follows from Tito there. Here we also learned a very important concept, which is partitioning diffraction. You want to apply Tito, but the problem is you are on the wrong hand side of the inequality, so you just simply did the trick of partitioning diffraction, and now you are on the right hand side of the inequality, and now by Tito you're done. Finally, we did this question in which we want to apply Cauchy, but first of all we needed to clear denominators, but after that we just applied Cauchy in the correct way, and everything followed smoothly. Alright, my friends, so that's it for today. In the next video we'll be wrapping up, hopefully, the Cauchy and Tito inequality. So don't forget to like, share and subscribe to my channel, and see you guys in the next video.